Thank you for joining this course developed by Biochem Academy. In the coming slides, we will be looking at the biology behind hemophilia A. Specifically, we will cover the genetics, the biochemistry behind the disease, and look at its effect at a physiological level. Next, we will go through the methods used to diagnose and monitor hemophilia A patients. And finally, complete the course with some key therapies that are in the market, as well as look at some of the upcoming therapies for hemophilia A. So hemophilia is a bleeding disorder that results in prolonged or excessive bleeding. Hemophilia can be divided into two groups, A and B, with the most common type being the hemophilia A, which is what we will be discussing in this course. So hemophilia A has an incidence rate of about 1 in 5,000 to 1 in 10,000 males, depending on the region. Now, I said males because the disease affects males and rarely females. The reason for this is because the gene that causes hemophilia is located on X chromosome. Now, what you see in this figure are the chromosomes from a male subject. So there are 22 pairs of non-sex chromosomes and one pair of sex chromosomes. So we have X and Y chromosome, right? And the gene responsible for hemophilia A is located here at the X chromosome. Also, because hemophilia is a recessive disorder, for females to have the disease, they would need both copies of the gene to have the mutation or variant. Now, females have two X chromosomes, as you can see here in this figure at the bottom right. Now, this means that females have two copies of the gene that causes the disease, the gene that causes hemophilia A. And hence, if one of the copies is mutated or faulty, then they have the other copy to make the protein coded that is functional. So what this means is that if one of the X chromosomes in the female have the mutated gene, they become carrier of the disease. Carrier meaning they don't show the disease, but have the capacity to pass on the mutated form of the gene onto their children. Now I will demonstrate how they can be carriers and pass it on to their children with this Punnett square. So as we know that we have two copies of each gene, one comes from the father and one from the mother. Now in the case the mother is carrier for hemophilia A, which is demonstrated by this red X that you can see. So the red X is the gene that is mutated or has the disease-causing variant for hemophilia A. So now once the genes are passed onto the next generation, there will be two offsprings or children that have the mutated gene from the mother. And that is demonstrated by passing of this red X onto the offsprings. Now the offspring shown in the top two squares are females, as they have two X chromosomes. So one of them will be a carrier. The other offspring at the bottom two squares that you can see are males, as they only have one X chromosome, and the other is the Y chromosome. So if they only have one copy of the X chromosome, they have nothing else to rely on, unlike the females. In this case, one male, or the offspring, that gets the mutated copy of the gene from the mother ends up having the disease, okay, which is hemophilia A. which is shown by this red box that I've just made around the male offspring. The gene we have been discussing in the last couple of slides, which is responsible for hemophilia A, is the factor VIII gene, which translates into factor VIII protein. Now, hemophilia patients demonstrate different severity in the disease. What I mean by that is that most severe patients will tend to bleed more aggressively than those with lesser severe disease. And patients that have the factor VIII protein activity less than 1% are usually categorized into the severe hemophilia A state. I say usually because physicians tend to take other factors into account, okay, such as bleeding episodes and so on. Now again, in hemophilia patients, activity of factor VIII between 1 to 5% are classed as moderate, and 5 to 40% are mild hemophilia A patients. Okay, so the factor VIII protein is a coagulation factor. So it's part of the coagulation cascade. What I mean by coagulation cascade? Well, it's a series of steps, hence it's called a cascade, that leads to the formation of clots. The primary function of the coagulation cascade is to maintain the integrity of the endothelium while preserving vascular patency. So endothelium is the inner lining of the blood vessels shown by this arrow. And what I mean by vascular patency is the degree to which the blood vessels are not blocked or obstructed. So this is the main aim of the coagulation cascade. Now let's look at the coagulation cascade and see how factor VIII functions at a physiological level.